Alrighty. I'm good. Thank you for asking. Hope you are well as well. And as always, just let me know if you have any questions at any point. I'll be monitoring the text thread. So to pick up where we left off last time, we were discussing a variety of different nucleophiles attacking carbonyl carbons. Right? We were talking in chapter 20 about aldehydes and ketones and how aldehydes and ketones are electrophilic. We said there's induction to withdraw electrons and create a partial positive. There's also resonance that creates even more partial positive. And so any decently strong nucleophile and a negative charge on a carbon is a really strong nucleophile. In this case, it's not as strong as most negatives on a carbon for a couple reasons. One, because it's in a relatively compact sp orbital that holds a negative and stabilizes it close to the carbon's nucleus. And two, because there are 3 pairs of electrons withdrawn away from that carbon by the more electronegative nitrogen, and that creates some partial positive on the carbon to balance out the negative. So this is really only a partial negative when you consider the electronegativity effects, but it's still enough negative on a relatively low electronegative atom that's somewhat unstable. So that will attract to the partial positive on the carbonyl carbon, and a nucleophilic attack can occur. When it does, produces a negative on an oxygen, which should be more stable than the negative on the carbon. But if a proton source is around, then the oxygen can pick up a proton, and that can give you this cyanohydrin. So this is a cyanide group, and the hydrogen is, or hydrin is reminiscent of a component of water. So the cyanohydrin is the product of that reaction. And this is a nice reaction. It adds a carbon to the molecule, right? Because we're adding this carbon in here. The CN group is a group that can undergo subsequent reactions after this to convert this into other functional groups. So it allows us to introduce a carbon into the structure and control the variety of the resulting functional group somewhat. The problem is that hydrogen cyanide is a gas at room temperature, and if I have it in solution, it can start bubbling out and evaporating, and it's extremely toxic gas. So this reaction typically would not be performed unless you had very specific equipment to handle that gas, and so that's a big disadvantage of this reaction if you wanted to use it as part of a synthesis. Just to point out a couple of the reactions that can occur subsequently after the cyanohydrin formation. At the CN group, LAH can be used. So the hydride that's bonded to the aluminum, we know is a great nucleophile. So a hydride can pull electrons away and attack the carbon, push these electrons to the nitrogen. That can happen again, pushing another pair to the nitrogen. So that makes a -2 charge on the nitrogen, which is really quite unstable. And as soon as any protic source is around, that nitrogen will pick up protons and become an amine. So this is one route, at least on paper. Obviously, there are practical challenges with the toxicity of the cyanide and hydrogen cyanide gas, but this is one route to forming an OH and an NH2 on adjacent carbons or on neighboring carbons. The cyano group, once it's connected, isn't really dangerous anymore necessarily because it's the CN minus ion that has a toxic effect biologically, as far as I'm aware. But once this is connected, another reaction that can occur at the CN is a hydration type reaction. So in this reaction, We're going to discuss the mechanism of this later in chapter 21, but just to give you a general idea of it, if I have a CN group here, what's going to happen is the H plus is going to protonate this nitrogen. So it's going to be protonated a number of times to make it into a leaving group. And this would also be done in water. And the water would be in a large excess. That's the solvent in which H3O plus is usually dissolved. The water would be attacking here and pushing electrons here once this is protonated first, right? So we have an acidic condition that protonates, creating positives. And then the water would attack, push electrons there. Then the water would be deprotonated. This nitrogen would be protonated again. Another, the oxygen would swing electrons in and push more electrons to the nitrogen. So eventually, all these electrons would be pushed to the nitrogen after it's protonated over and over and over again. And when one oxygen attacks and then another one attacks, in order to push that out, you end up with two oxygens connected to the carbon. So we'll see the detailed version of that mechanism later. So I won't expect you to draw it on next week's exams necessarily, but just wanted to give you an idea of how and why that works, maybe to help you, hopefully help you remember what these conditions will do to a CN group and what the resulting structure would be. Another reaction that carbonyl compounds undergo is the Wittig reaction. And the Wittig reaction is a really nice reaction for synthesis. It will, like the Grignard reaction, connect two carbons together. So the idea here is you have a carbon on one structure and a carbon on another structure, and you're getting one to attack the other, right? We already know the carbonyl carbon is electrophilic, and we know carbons that have some quantity of negative charge are nucleophilic. So this is very similar to the Grignard reaction we talked about. So what are the main differences? Well, the Grignard obviously involves a carbon sharing electrons with magnesium. There could be R groups here, or hydrogens, could be part of a double bond or an aromatic ring. But since carbon's more electronegative than magnesium, there's a large partial negative there, and so that would come in and attack and push these electrons up. Then that oxygen would have to pick up a proton, so I'd end up with an OH here. But what's interesting about the Wittig is as this carbon attacks and pushes electrons up, they don't just stay on the oxygen, because the Wittig reaction involves this compound which is called an ylide. And the ylide has a positively charged phosphorus right next to the nucleophilic carbon. So part of the role of that phosphorus is to create some charges that attract to stabilize the structure, and also to create an alternative resonance contributor where these electrons can swing in there and create a double bond, since phosphorus can accept more than 8 of valence electrons in its outer energy level, can have more than 4 bonds. So these two structures would be in resonance. That helps to stabilize the negative and make it easier to form it. But there's still a large partial negative on this carbon to allow it to attack. So when it does attack, the electrons that normally would swing out to the oxygen are going to swing out to the oxygen, and it's going to use them to attract and bond to the phosphorus. And then that's going to eventually result in a double bond. So we're going to investigate this reaction in some detail as we move forward here. So obviously this carbon is the nucleophile, and this one here is the electrophile. So as we said, the ylide, which is one of the reagents in the Wittig reaction, there's a negative formal charge on this carbon in one resonance contributor, and it doesn't have any charge in the other. So if we think about the resonance occurring, we know neither of these structures exists. What exists is the resonance hybrid. So if we were to imagine the hybrid or average of these structures would depend on which structure is a major contributor. So for a long time I had a misconception about this reaction, and you may form the same misconception in your mind if you're not careful here, and that is when you look at these two structures, This one doesn't have any formal charges, so it looks significantly more stable than the other one. And we see phosphorus forming 5 bonds in a lot of different compounds. There's nothing inherently unstable about that, although maybe it's not quite as stable as it could be because it doesn't have a noble gas configuration exactly. But this is the major contributor, which means that the hybrid, also just to note, pH means phenyl. So this pH is actually a phenyl or aromatic ring, and we just usually abbreviate that with pH to save time and space. And that was a very sloppy ring. But the issue here are with the resonance hybrid, there would only be a partial negative and a partial positive. But it's a very large quantity of charge here because the major contributor has full formal charges in it. So why is this the major contributor? So first of all, the factors that stabilize the negative charge, one is the resonance. And so instead of having full formal charges, we really only have partial charges because the resonance spreads the negative out between the carbon and phosphorus a little bit. And also having opposite charges on adjacent atoms also really helps to stabilize it because they form a charge attraction. Oops, why that happened? I don't know. So we have a positive, negative attraction that those formal charges form because they're on adjacent atoms, specifically because they're on adjacent atoms. So why is this the major resonance contributor? Well, the main reason for that is orbital overlap, or really ineffective orbital overlap. Right? So we know anytime an element has a sigma bond with another element, it's the head-on overlap of their orbitals, right? So the carbon has an sp3 from the second energy level, and the phosphorus has an sp3 from the third energy level. So the phosphorus's orbital is larger, and that means these elements can only get so close. So when the p orbital of the carbon and the p orbital of the phosphorus, which is the 3p, try to overlap, they're not close enough, and the carbon's p orbital is smaller and more compact, so it kind of would overlap with the thinner part of the p orbital rather than the meatier part of it. So there just isn't effective orbital overlap between the adjacent side-by-side p orbitals that would be needed to form an effective pi bond. So even though we can draw a pi bond in the Lewis structure, we have to remember that the pi bond results from side-by-side p orbital overlap, and it's not an effective orbital overlap if the p orbitals are in different energy levels on the atoms. So for that reason, the double bond here is not as stable as you would normally expect a double bond to be, and the major contributor is the one with the charges, which means the resonance average includes large partial charges there. Very large partial charges and a very large negative on a carbon is relatively unstable, and so it's going to use that pair of electrons to attack the electrophile. And so the idea here is to set this up so it attacks the electrophile. The electrons swing out. Normally we would think about them swinging onto the oxygen to make a negative there, but instead they'll swing directly to the phosphorus and make a fifth bond to the phosphorus. So the advantage here is we're converting a pi bond into a sigma bond, one advantage. Also, the phosphorus-oxygen bonds are quite stable. So you see phosphorus bonding to oxygen a lot in nature because those bonds are especially stable. We're also, in this first step, the advantage is we're also stabilizing this negative by allowing the carbon to form a new bond there. So there's a lot of reasons why this would go forward. The disadvantage of this step is it forms a four-membered ring. So we know the four-membered ring has a lot of angle strain. and torsional strain. So that's going to be pretty unstable when that forms. And so as soon as that forms, intramolecularly, it will break apart. And so these arrows show the oxygen pulling electrons away from the carbon to form this structure, which is in resonance with this. Right, so this is the same situation we just looked at, where if you have a second energy level atom like oxygen or carbon trying to form a double bond with a third energy level atom like phosphorus, the side-by-side pure overlap is not very effective. So actually, the best way to show this triphenyl phosphinoxide product is with the charges here. This is the major resonance curve, but you'd also see it often shown this way, even though that's the minor resonance contributor. The phosphorus oxygen bond is quite stable there, and so that helps to drive that reaction forward. At the same time, the carbon pulls electrons away from the phosphorus, since it's more electronegative than phosphorus, and uses them to share with the other carbon, since this carbon here is losing the electrons the oxygen's taking, and that makes a carbon-carbon double bond. So the Wittig reaction converts a carbonyl into an alkene. Right, so we have 3 carbons here, and we have a CO double bond on carbon 2. Basically, it's kind of like the opposite of an ozonolysis. Right? In ozonolysis, we start with an alkene, we break it, and we form CO double bonds wherever the alkene broke. In a Wittig reaction, we start with the CO double bond, we go through this mechanism and make a new CC double bond. And so that can be used to add 1 additional carbon to the structure, or these hydrogens could also be R groups. So really this is a nice reaction where we can connect 2 large molecule fragments into one structure, and in one step really increase the complexity of our structure in a very significant way. So here, this is the slow step. Obviously, it's intermolecular. It forms a relatively unstable intermediate with lots of angle strain and ring strain. And this is a much faster step due to the opening of the ring, alleviating that ring strain and the formation of a very stable phosphorus-oxygen bond that forms there. And that being so stable is one of the things that drives this equilibrium forward toward the product side. Even though a CC double bond is not as stable generally as a CO double bond. So that's a disadvantage for this reaction, which would, if we just focused on that, it would be more likely to be reactant favored. But starting with this unstable ylid helps to drive the equilibrium toward the formation of the CC double bond, because it also forms this relatively stable phosphorus-oxygen bond. So we need to also talk about how to make the ylid. We just talked about putting this in there. I don't know if this is something you can readily buy because it is relatively unstable. It might be difficult to buy it and store it for a very long period of time, or even to just because it's so expensive, it might be expensive to purchase, but you can also make the ylid. So what you do is take triphenylphosphine, which is this structure. Again, the pHs represent aromatic rings, so triphenylphosphine looks like this. That's a very inexpensive compound you can buy. And then you just need an alkyl halide, or some leaving group connected here. It doesn't have to be on a methyl, but it can't be too crowded, right? Because these aromatic rings are pretty bulky. So if I'm going to expect these aromatic rings connected here to not create too much steric hindrance, so that this phosphorus can come in here and bond to the carbon and push out the leaving group in an SN2 in one step, I can't have too much steric hindrance there. So that is a limitation. This reaction is definitely going to be slowed down a lot the more steric hindrance there is around this carbon. So Once that reaction occurs, to make the ylide, you add this very strong base, butyl lithium. Right here, you can buy this. It's not cheap, but you can buy it and and react that with this compound. So this negative on this carbon is quite unstable, as we know negatives on a carbon, especially if it's in a more elongated sp3 orbital, which this one would be. It's not held that close to the nucleus. It really needs to be shared with something to be stabilized. So that's going to pick off a proton, and then the electrons would stay here, because here the negative charge is stabilized by resonance, and it's stabilized by being adjacent to a positive charge versus over here. So this second step here is very fast. The first step is a substitution. It's a simple SN2. There is some limitations on how sterically hindered this can be for it to work. But the second step, this proton transfer, is very fast and very product favored, because the negative on this carbon is stabilized through resonance, and the attraction here is much more stable than the negative over here. So once the ylide is formed, and we need a very strong base to do that, because this negative is pretty unstable, and we need to start with something even more unstable if we want to make that reaction forward favored. We can imagine doing a Wittig reaction to connect two large structures together into one. And so from a synthetic perspective, the idea here is if we want to make an alkene, or double bond between two carbons, retrosynthetically we would disconnect those two carbons. It's kind of like an ozonolysis, but if I did an ozonolysis, the ozonolysis would break that in a forward reaction, and you'd form two CO double bonds. So one of the structures is the same as what we would start with in the Wittig reaction. So you can think of that retrosynthetically, right? If I ask you to make a structure using a Wittig reaction, you'd work backwards, disconnect there, work backwards. One of your carbons from the double bond would become a CO double bond, and the other would become an alkyl halide. And so what you would have to do here is start with the alkyl halide, react that with triphenylphosphine, and then the butyl lithium. The triphenylphosphine would come in, push out the bromine. The butyl lithium would pick off this proton, and so that would give you the ylide. Which would have this carbon be nucleophilic, right? So that's how it's going to make the connection. Then this structure here would be added, and that attack would occur. And then these electrons, instead of swinging out to the oxygen, they would swing out and connect to the phosphorus. So that would give so now this carbon is connected to this one. And the oxygen, man, I really did not try that well, is going to be connected to the phosphorus. So that's the four-membered ring that forms. Then the oxygen rips the electrons away from the carbon, and the carbon rips electrons away from the phosphorus due to the electronegativity differences, and that produces the pi bond and the triphenylphosphine oxide, which is then a separate byproduct. So retrosynthetically, we can also imagine a different set of reactants, right? So we said if we want to try to make this compound, this is our synthetic target, we would disconnect here retrosynthetically, and we could make one of those carbons a CO double bond and the other an alkyl halide. So we would treat the alkyl halide with the triphenylphosphine, then treat it with butyl lithium, then add the carbonyl, and that should produce the product. Alternatively, we could have made the other carbon of the pi bond, the carbonyl, and this carbon could have been the alkyl halide. And we do the same thing. Start with the alkyl halide, add triphenylphosphine to push that out, add the butyl lithium to depronate here, and then have it attack and make the four-membered ring, and then when that ring opens back up, it should give the same product. So in this particular instance, the carbonyl and alkyl halides are on secondary carbons either way. So these two routes are equally plausible, and there's no reason why on paper one would work better to produce this product than the other. So let's take a look at the quiz question then that relates to that. Retrosynthetically, if we want to make this target, we want to synthesize this compound through a Wittig reaction, what would we use? Well, I can disconnect here. When I disconnect and look at these two carbons, I notice one is a secondary carbon, or at least it will be once it's disconnected from the other. And the other one is a primary carbon. So in this case, there are a couple options, but one makes a little more sense than the other. Specifically, whichever carbon is less crowded, that's the one where I want to put my alkyl halide, and I want to put the carbonyl on the other one. Because a carbonyl carbon is flat, it doesn't have much sterics. It's easy for things to attack the top or the bottom of that flat structure. But with the alkyl halide, that has to be attacked by the triphenylphosphine. And so we want that to be as open or unsterically hindered as possible, right? So we could imagine this option, or we could have made the same disconnect and put the alkyl halide here and the carbonyl carbon here. That might also work, but it's probably not going to it's probably not going to be as fast kinetically, because what has to happen here is the triphenylphosphine, which is kind of crowded, has to come in here and push out the leaving group. Here, though, it's primary versus secondary alkyl halide, so it's much easier for the triphenylphosphine to come in there and push that out. So what would I do to make this product? I would start with the alkyl halide that makes the most sense. I would first treat it with triphenylphosphine. That would come in, push out the leaving group, produce a triphenylphosphine connected to that carbon instead, which now is positively charged. Then I have to add butyl lithium. The butyl lithium will deprotonate here. So you're probably also noticing at this point, if this carbon had been tertiary, this won't work. Right? On a tertiary carbon, it's a lot more crowded. So first of all, we can't even really get the triphenylphosphine to attack and push the leaving group out. But we could imagine the leaving group leaving first, which would produce a carbocation. Then the phosphorus could attack. But even then, if there's no proton here to pick off, we can't do the next step. The butyl lithium has to be able to pick off a proton to produce the ylide. And if there's no proton available, because these are all R groups, like methyl groups, the reaction can't continue. Right? So won't obviously work on a tertiary alkyl halide. Secondary is also not optimal because of the sterics. Primary is the best. So the triphenylphosphine come in and push that out. Butyl lithium would deprotonate. That would give you triphenylphosphine next to a negative charge and a lone pair there. And then that would attack here, pushing these electrons out to the phosphorus. So the third reagent would then be the carbonyl compound. That would attack. It would attack back at the phosphorus, form the four-membered ring. And then when that opens up, that would give the product. So the four-membered ring would look something like this. So this carbon would attack. There's my five-membered ring. When that carbon attacks here, the electrons swing out to the oxygen and they attack the phosphorus. Oops, that shouldn't be a positive charge. I'm trying to figure out why the molecule is suddenly overall positive. Yeah, there's no charge on a phosphorus. It has 5 single bonds. So then the oxygen would pull these electrons away to form a phosphorus oxygen double bond, and the carbon would pull these away to form the pi bond there. So that would give you the product. All right, so that covers the Wittig reaction. Next reaction that we want to talk about briefly that occurs at aldehydes and ketones is the Baeyer-Villiger reaction. This reaction is kind of unusual for a couple reasons. So let's take a look at the mechanism. So in the Baeyer-Villiger reaction, you use this peroxy acid. So this is similar to what we use to make epoxides. So if you recall, we used peroxy acids before, and that was when you have an alkene, you use peroxy acid, specifically MCPBA, which is an example of a peroxy acid. MCPBA looks like this. It's got a chloro meta to the benzoic acid. So carboxylic acids have COOH. This has COOOH. It's got an extra oxygen in there. And we talked about how unstable that oxygen bond is. And so that gets rid of that oxygen and installs it there, bonded to both carbons to make an epoxide. So if you have an alkene and you use a peroxy acid, you make an epoxide. If you have a carbonyl, like an aldehyde or ketone, and you react it with the peroxy acid, it goes through this mechanism here. So even though this oxygen only has a partial negative, and this carbon only has a partial positive, this can attack here. It won't attack very often, and this first step is quite slow. And we said usually if I've got two neutral species, if one attacks the other and shifts electrons to form two charges, two formal charges here, that's going to be way less stable. So this first step is pretty slow. And you might need some heat to facilitate it and get through the transition state often enough to get to the products. But if a few molecules go through this once in a while, the next couple steps are very fast in comparison, and they're quite product favored. So what would happen here is an intramolecular proton transfer. This happens intramolecularly because there's a 5-membered transition state. So if I count the atoms, 1, 2, 3, this oxygen here is 4, and the hydrogen is 5. That is enough atoms for the structure to bend around. If the bonds rotate just right, this oxygen and this hydrogen here will be quite close together. And the partial negative on the oxygen can pick up that proton. So the proton transfer, electron staying behind, gives you the next intermediate. The proton transfers are almost always fast. Intramolecular proton transfers are fast if it's a 5 or 6 membered ring transition state, because those atoms are naturally going to be rotating close to one another to do the proton transfer. And then the next step involves electrons swinging in, and then one of the R groups could also be a hydrogen, but one of the things bonded to this carbon, which was the carbonyl carbon initially, is going to transfer over to that oxygen. So here's a rare situation where a carbon acts as a leaving group. And we say, normally we would say, if I've got a negatively charged oxygen, like I have right here, and there's R groups or hydrogens, that normally is unreactive. Maybe it'll pick up a proton if there's a protic source somewhere, but we can't usually swing that back in because these R groups and hydrogens can't stabilize the negative. They can't leave. So we can't swing the electrons back in. But in this case, since there's an oxygen here nearby that has a leaving group, and this here is a great leaving group, because if the electrons leave and swing out here, it'll stabilize this positive, and that produces a pretty stable byproduct or side product from the reaction. It's more of a byproduct because it's produced intentionally, but we can remove it later. So what's going to happen here is when the electrons swing in, this R group is going to migrate over to this oxygen, and that's going to cause this group to leave. This is the leaving group. So the R group, you can think of a leaving group, but it's more like a hydride or a methyl shift, right? And we've seen that occur a lot. A carbon or hydrogen atom can grab its electrons away from another carbon and shift over to the next atom. If there's a leaving group on that atom, or if there's space for it. So the leaving group allows the R group to shift over and swing electrons back in. And so basically the net effect of this reaction is it inserts an oxygen between one of the R groups or hydrogens attached to the carbonyl carbon. It inserts an oxygen between that group and the carbonyl carbon. And so this converts a ketone or an aldehyde into an ester. So if you do this reaction, and people have obviously done this experimentally with a variety of different R groups, including hydrogens, and measure the rates of reaction, you can show which R groups are most likely to migrate. And so that's what we're seeing here. Oh, actually, that's on the next slide, sorry. We talked about this one being the slow step. Why is it? Because we're forming charges. Forming two formal charges from two neutral species. And while this step is reversible because this oxygen could pick that proton back off and go back in the reverse direction, the last step is not reversible. We're not going to see this carboxylic acid group come back in to here and push this R group over here and push these electrons up. That would take two neutral species and form two charges, and it would form an unstable oxygen-oxygen bond. So this is very stable and low in energy compared to this substance. And so this process is really only in the forward direction. We would never really see that go back. And so that's nice. If we have a series of equilibria steps, and then the last step only really happens in the forward direction to any significant extent, that helps to, through the Chaillet's principle, to pull all the other steps forward. It's just a matter of how long it will take if the first process is relatively slow. So when it comes to which groups are most able to migrate, this is the order that shows which groups are most likely to migrate. This is on your formula sheet. So hydrogen is greater than tertiary, greater than secondary, etc. That means hydrogen migrates the easiest, most readily. Then a tertiary R group, then a secondary R group, then a phenyl or aromatic ring, then a primary R group, then a methyl. Methyl is the slowest. So this is on your formula sheet. You don't have to memorize this order. It's not really easy to explain this order, but it is what we find experimentally. So that's the highest likelihood of groups to migrate versus lowest likelihood of groups to migrate. So we can use this to predict the outcome of a reaction, because if I have two different R groups connected to my carbonyl carbon, I have to be able to know which one's going to migrate in that key step of the mechanism. So if we look at the mechanism back here, first thing that's going to happen is the oxygen that has a hydrogen is going to attack the carbonyl carbon. So it's going to be this oxygen to attack the carbonyl carbon, pushing the electrons up. Oops. So that gives a negative. This oxygen then is now connected here. This is a little bit tricky. You want to show the bond angles here such that this oxygen over here can grab that proton. But that does create a positive, so this is kind of unstable. So the next step is the proton transfer we saw. So this oxygen here should pick up that proton. They're 1, 2, 3, 4, 5 atoms away. It's very likely that those atoms will be in the right proximity to do that proton transfer. These electrons will stay here to balance out that positive. So that proton might be shuttled back and forth a little bit. Over here, it can be, the positive charge can be stabilized by resonance, not here. Right? So that's another factor why this step would generally go in the forward direction. So then next thing that's going to happen is going to be the migration step. So we have to consult this order. Right? So on one side of the what was once a carbonyl carbon, we have a methyl group. And on the other side, this is a secondary carbon. So really, at the moment, it's tertiary because it's bonded to 1, 2, 3 carbons. But as a group, once it migrates, it's basically a secondary carbon because it has 2 carbons within that group. And so the secondary should migrate faster than the methyl. So we're going to show the migration occurring then. This group of pair electrons would swing in here. And the secondary carbon here, with the electrons it's sharing, is going to jump onto this oxygen, and then that will break this bond. These electrons will swing in here and push these up to that oxygen. So this step has 4 arrows. It's a tricky mechanism because it's kind of different from the other mechanisms we've seen. So you might want to do a little extra practice with it in case you get asked about it. So when these electrons swing in, that's going to form a CO double bond there, balancing out that charge. The methyl group's still here. This group migrated over and now is on this oxygen. So the oxygen is still there, and now this carbon is now bonded to that oxygen. So that's one product. That's the main product we're trying to make, right? We're trying to take this substance and basically insert an oxygen in between the carbonyl carbon and one of the R groups, which is basically what we did right here. And then the byproduct is when these electrons swing in there, it'll form a CO double bond there. These electrons swing up, I'll have an OH. So I always get acetic acid as a byproduct. That can be removed because if I add a base to pick off that proton, this will become charged and it'll go into the aqueous layer, whereas this relatively low polarity structure would, due to the large R groups here and here, end up primarily in a low polarity layer. So you can separate those through liquid-liquid extraction. All right, so that gives us a couple new reactions that make changes to the carbon skeleton or the skeletal structure in general of the molecule. And so now this allows us to consider how these reactions can be recognized when they're useful in solving syntheses. Right? So anytime we solve a synthesis problem, first thing we want to do is to check to see if the carbon skeleton is changing. Right? So if I have a certain structure, a certain number of carbons, and I'm trying to make some other compound, I want to see if there's an addition or a subtraction from the number of carbons in the structure. We know the Grignard can be used to introduce more carbons. We now know the cyanohydrin reaction can be used to introduce one extra carbon. And the Wittig reaction can be used to introduce extra carbons as well. So just to point out, in the Grignard, really any R group could be bonded to this magnesium bromide. So it doesn't have to be a methyl, obviously. So I just cross this out. Any R group could be here. And that really allows for a lot of flexibility. If we want to make an alcohol with a specific R group nearby, the Grignard is a great way to do that. The cyanohydrin reaction only introduces one extra carbon to the structure. The Wittig reaction could introduce also a variety of different carbons. So these hydrogens could also be R groups. So you can connect those R groups initially on the ylide, and then when that attacks the carbonyl and the four-membered ring breaks open, you form the pi bond. This gives you a lot of flexibility in terms of making an alkene. So if you have an initial carbonyl or alkyl halide, and you want to convert that into an alkene that has more carbons than it had initially, because now we have 7 in this case, or it could have been more if we had some R groups connected to the carbon 7. That is a good sign that the Wittig reaction might be a good bet. Right? So this is a Grignard, cyanohydrin, and Wittig. Grignard. And then the Baeyer-Villiger reaction we just talked about a couple minutes ago. That's pretty different from the reactions we've learned so far, and so it's not too difficult to recognize when you need it. But if you have a carbon skeleton that's not really changing other than the insertion of an oxygen between a CO double bond and a neighboring carbon group, excuse me, that's a good indication that you would use the peroxy acid that you need to do the Baeyer-Villiger reaction. All right, so here was the synthesis question from today's quizzes. The quiz question relating to synthesis. So first thing you want to do here, count the number of carbons, recognizing that we need to add 2 more carbons to the chain. And so there are a couple different ways you could think about doing that. You could think about using a Grignard. You could think about using a Wittig reaction. So there's a couple different approaches here that would work, and there's more. I saw in some of your quiz answers some interesting ideas that you all came up with that were different from the ideas I had, and most of that's legitimate, and I will be commenting on that in your Google Docs after the lecture. So one thing we definitely recognize, though, is we need to do something on carbon 4, obviously, right? Right now there's hydrogens here. We need to get rid of most of those and introduce the ethyl group and introduce the CN group. So we could think about working backwards, we could think about working forwards, and for me, probably what I would think about first is, what's the first reaction I can do here? Because there's no alkene, there's no leaving group, there's no heteroatom. Almost every reaction we've learned will not work on this structure because there's no reactive site on the structure. The only reactive site is this tertiary proton. And the only reaction that will really undergo, since there's no leaving group nearby or anything, is to react that with Br2 or NBS and light or heat. That will promote the radical reaction we saw in Chapter 11 at the beginning of the semester. The bromine radical will pick off abstract to hydrogen. One electron will stay behind to form the most stable carbon-free radical that the structure could form. And then that will pick up another bromine. So that's really the only reaction we can do. Regardless of what the product is, that's the only reaction I can do with this reactant from the reactions we've learned. So, I mean, that's got to be where I start. So now I can start to think about how to introduce something here on carbon 4. That does mean, since carbon 4 only has one proton in the end, I'm going to have to take some protons off. So, you know, the next idea might be removing one of those protons. So you could add a base, like a terbutoxide. And the O of the terbutoxide would be negative. It would pick off this proton, electrons would swing in and push out the leaving group. So that could form an alkene. So we are going to have to get this ethyl group to attack here. Right? This is still carbon 4. We want the ethyl group to connect to carbon 4. So we're either going to have to make carbon 4 into a nucleophile and have it attack, we'll call this 5, or make carbon 5 a nucleophile and have it attack 4. Either way, there is a way to do that. And so you have a couple options here. So one thing you could do here is add HBr across here to make carbon 4 connect to a bromine. If you use peroxides, that will produce the radical reaction we talked about in Chapter 11. That is the anti-Markovnikov addition across the pi bond. That's what we need if we want the bromine ending up there. And that puts a proton here, which is what we need in the end anyway. So now I could have an ethyl Grignard maybe come in and push that out to install my ethyl group. But I don't want to do that probably because, you know, if I use an ethyl Grignard and that pushes out the bromine, I've got the correct carbon skeleton, but I have no way to install the CN group. And so working backwards here, at least my instinct is to probably consider to install the CN group. Maybe initially there was a leaving group because the CN minus is a great nucleophile and it usually comes with a sodium or potassium counterion. It's just there to keep the charge balanced. But because that's a good nucleophile, it could come into a secondary or primary carbon in an SN2 and push out the leaving group and make that product. So the last step maybe involves installing the CN group to push out the leaving group. So this reaction down here, we're trying to meet here in the middle. It's probably not the best idea because then it produces an alkane again, and there's very few reactions that work on an alkane to put that group on there. So what I was seeing a lot of students do here, instead of putting the bromide on, they were trying to put an OH there because the students recognize that if you do this anti-Markovnikov hydration reaction, that would give you an OH there, and then that could be oxidized to an aldehyde. What's the purpose of that? Well, that would then allow this Grignard to attack, and there'd still be something connected there. There'd still be an OH or an oxygen connected there until it was protonated. So then that could be converted into a leaving group with a tosyl chloride or pyridine. So it wouldn't be a Br leaving group, it would be an OTS leaving group, but it's a leaving group nonetheless, which the cyano group could come in and push out to make the product. So that's one option. There's a variety of other options here. So that's one synthesis there. And I put these slides in to show the net overall synthesis. So this is the one I just showed. The Br2 would put a bromine here. The terpene oxide would eliminate to make an alkene. HBr with peroxides would do anti-Markovnikov, put a bromine here on the end. Magnesium could make that into a Grignard. Actually, oh, this is different from the one I just showed. All right, so it's the same in the first three steps. I would put a bromine here. But what I was thinking about on a minute ago was using a Grignard to attack that and push the bromine out, which is also okay, right? We got through that synthesis. But if we add magnesium here, that would convert that itself into a Grignard. And then we could have that attack a 2-carbon molecule. So here that would attack an ethyl bonded to a COH. That doesn't seem right. It seems like there's an extra carbon in there. Now that I'm looking at this, it doesn't quite seem to work. I think I need to fix that a little bit. Yeah, this isn't going to work the way it is, so you can kind of ignore that. There's actually a number of ways this can work, but this is not one of them. So if you were to make this part into a Grignard, you would have it attacking a 2-carbon group. So the ethyl plus one more carbon is a 3-carbon group. That's obviously not going to work. So we could have that attack 2-carbon aldehyde. Oops, I read 3-carbon aldehyde again. 2-carbon aldehyde. And then once you add the acid in the next step, so this would just be 2-carbon aldehyde here. Then the acid in the next step would protonate that oxygen. But then when I use the tosyl chloride to convert that into a tosylate group, it's not on the right carbon. So I can't just then use a CN to push that out. I'd have to use an ethoxide to pick up this proton, make a double bond here. Then I'd have to try to figure out how to add something across this double bond that would allow me to put the leaving group here. But in this case, since both sides of the double bond are equally substituted, if I were to use HBr or something to try to add a Br here, that could be putting a leaving group on the carbon I want, and then the cyano group could come in and push that out. I can't control which carbon the HBr goes to, so this synthesis has some issues. I should have been a little more careful when I put this one together. So this one works. Lots of steps here. Bromination, followed by terpene oxide, and then instead of the HBr, I could add this set of reagents to make the anti-Markovnikov hydration, then the PCC, methylene chloride, to oxidize that to the aldehyde. Then this Grignard could attack that to make this alcohol after it's protonated, then the tosyl chloride and pyridine, then this NaCN to push out that tosylate leaving group. And then an alternative that has even fewer steps, and so this probably might be the ideal way to get through the synthesis. It starts off the same way. First two steps are the same. So after the first two steps, you would make the alkene. Right? The first one would install the bromine here. The second one would eliminate that to make the alkene. So then in ozonolysis, normally we don't think about these in the synthesis because an ozonolysis decreases the number of carbons rather than increases it. But an ozonolysis here would break that double bond and make a CO double bond. And as we said earlier today, if you have a carbonyl, you can add more carbons to that, not just through a Grignard, but also through a Wittig reaction. So this molecule here is the ylide. And so if we look at that, oh, it's got triphenylphosphine on it. So this would be 3 phenyl groups on a phosphorus, and that'd be bonded to a carbon with an ethyl and a hydrogen. And that's implied then that that carbon has a negative charge. Right? So this is my ylide. So that would attack here. These electrons will swing out to the phosphorus. That would form the 4-membered ring, which would break open by the mechanism we talked about. And that would give an alkene there with 2 more carbons. So now I have an alkene that is asymmetrical. There's one side that has extra hydrogen, the other side substitute with carbons. So now I can get the bromine at the right position. If I add HBr without peroxides, the H would go to the H hydrogen where there's already an H, and that would be a Marconic competition. The bromine would be here. That's not what I want, right? I want the bromine right here on the same carbon. The CN is going to come in so that the bromine can leave when the CN replaces it. So if I use HBr with peroxides, that would do an anti-Marconic addition and put the bromine in the correct position. And then the CN minus from the NaCN can come in and push that out in an SN2 to give the product. So a couple different options there. I probably would not give you a synthesis on an exam that required so many steps, but you should definitely practice enough. So hopefully you're able to solve a synthesis if necessary that has 4 or maybe 5 steps maximum to get through it. And so then the last section of chapter 20 is about spectroscopy. So most of this is a review. We talked last semester a lot about how the CO double bond stretch comes right around 1700. And I don't expect you to recognize subtle differences in the exact position of that stretching frequency in the IR spectra, but you should know because the CO double bond is so polar that you usually see a big, strong signal somewhere close to 1700 if you have a CO double bond present in the structure. If you don't see that signal somewhere around 1700, that's a big, strong signal. You probably can be pretty confident there's no CO double bond in your structure. If you have an aldehyde, in addition to the signal around 1700 in the IR, you would also see this carbon-hydrogen stretch. And because this is an sp2 hybridized carbon, the sp2 hybridized carbon-hydrogen stretching frequency usually comes a little above 3000, but this one comes actually significantly below 3000. So that's an anomaly that you want to be aware of as well. NMR, talked about that a lot last semester, and we know, you might be expected to predict splitting patterns and shifts and integrations. So all of that still applies. The main thing about CO double bonds is how they affect protons and carbons that are near them. So if you have a ketone, you want to be aware that any carbon that's one away from the carbonyl carbon those protons are going to be slightly de-shielded by the oxygen pulling electrons away, which pulls a little bit of electrons away here, which pulls a tiny bit of electrons away there. So that slightly de-shields the hydrogens and causes their shift to be increased by about 1 ppm from where it would normally be. In addition, and for an aldehyde, an aldehyde proton usually comes around 9 or 10. Why is this shifted so far downfield, almost to the end of the spectra? Well, that's because it's on an sp2 hybridized carbon. Normally we expect protons in an sp2 hybridized carbon, like if it's an alkene, to occur between 4 and 6. But if there's an oxygen nearby that's strongly de-shielding, that will really pull a lot of electrons away, right? So this hydrogen is 1, 2, 3 atoms away from the oxygen. This one is 1, 2 atoms away from the oxygen. That one atom closer really causes the electrons to be pulled away from it a lot. So it's very de-shielded, and its nucleus, there's a big energy gap between the two magnetic spin states for it when it's so de-shielded, and so that causes it to shift to a much higher energy side of the NMR spectrum. You should be aware that the carbon NMR for aldehydes and ketones, if I've got R groups here or a hydrogen in an R group, those carbons in the carbon NMR usually come all the way down around 200. Again, they're sp2 hybridized, which normally comes between 100 and 150, but if it's directly connected to an oxygen, it's going to be greater than 150, often all the way down to around 200 ppm. All right, so let's see if we can apply these ideas to the structure. So if we're dealing with shifts for the proton NMR, we would want to draw in all the hydrogens. Make sure we figure out how many signals there are. So there's no chiral center here, so these two hydrogens should be equivalent. They have the same environment due to the structure around them being equivalent for the hydrogen that's pointing out at you versus the hydrogen that's pointing away. Same thing here, these two would be equivalent. Call this one C, there's no proton here. Here we could call this one D. And then same thing here, these two are equivalent as well. So we have five different types of protons there. So if we're looking at the shift, hydrogen A, it's a methylene or a CH2. So normally that comes around 1.2, but it is 1 away from a CO double bond, so that's going to cause it to be increased by about 1 ppm. So probably between 2 and 3. And we could say the same thing about the protons over here, except they're also 1 away from a CC double bond, which also causes de-shielding and shifts it down by about another ppm. So hydrogens of type E would probably be between 3 and 4. The hydrogens of type B, too far away from this oxygen to be affected by it, too far away from that oxygen, but they are allylic to the pi bond, so we'd expect those to probably be between 2 and 3 as well. D is on an alkene, so that's normally between 4 and 6. In this particular case, the alkene is in conjugation with the CO double bond, right? We know there's a minor resonance contributor here that puts a carbocation here, and so that could also shift these electrons over and extend the carbocation here. So due to resonance, the electrons are really de-shielded or pulled away from hydrogen D. So we expect that probably to occur to closer on the more de-shielded side of the 4 to 6 range. And then lastly, an aldehyde proton is usually around 9 or 10 ppm. So that would be the shift. What about the splitting? Hydrogen's A, there's nothing here on this neighboring carbon to split it, but B would be splitting it, and there's 2 of those. So we'd use the n+1 rule. That would give me 3, so I'd expect that to be a triplet. Hydrogen B, same thing. There's nothing on this side to split it, but it's split by A, and there's 2 of that type. So 2 plus 1 makes that a triplet as well. hydrogen C. Normally aldehyde protons don't get split even if there is a hydrogen on the neighboring carbon because the coupling constant's usually too small. But here there's no hydrogens on the neighboring carbon anyway, so we definitely expect that to be a singlet. No splitting would occur there. D would be split by E. There's nothing here. So 2 plus 1 would split that into a triplet. And E would be split by D. There's only one hydrogen of type D to split it, so 1 plus 1 makes that a doublet. And then the integration is very straightforward. It's just the number of hydrogens of that type. So the integration would be 2, 2. There's only one hydrogen of type C, so that'd be 1. There's only one hydrogen of type D. And there's 2 of type E. For the carbon NMR, I redraw the structure here. Carbon NMR, we want to look at the carbons. So there's 1, 2, 3, 4, 5, 6 in the ring, and 1 outside the ring. 7 carbons. So we want to describe their shifts. So carbon 1 and 7 are aldehydes and ketones. So they're probably going to be around 200 ppm. They're extremely de-shielded. Carbons 4 and 5 are alkene carbons. So we expect those to be between 100 and 150. Oops. And so that leaves carbons 2, 3, and 6. And none of those 3 carbons are directly bonded to anything that's very electronegative. So if I have an sp3 hybridized carbon that's bonded to something very electronegative, like an oxygen or nitrogen, that's usually going to come between 50 and 100. If not, maybe it's a couple atoms away, or there's no electronegative atoms right nearby. If that's sp3, I would expect that to be between 0 and 50. It could be closer to 50 if there's something de-shielding, but somewhere in that range. All right, so there's another helpful NMR review for you to finish up chapter 20. All right, so chapter 23 is about carboxylic acids. We're a little behind in the lecture. Carboxylic acids are very abundant in nature, similar to carbonyls, similar to ketones and aldehydes. Carboxylic acids have relatively stable bonds. The CO double bond's pretty stable. OH bonds are pretty stable. And so these occur in a variety of naturally occurring compounds and synthetic compounds that are used in a variety of pharmaceuticals and different industrial purposes. In industry, this reaction is used to form acetic acid. Acetic acid is also a natural biological byproduct, but in a controlled, large-scale, millions of tons per year, scaled up, batch, this reaction, you would need a catalyst, and even if the catalyst is expensive, it can usually be regenerated and re-isolated and used many times. So that's an advantage. That produces acetic acid, and then acetic acid is converted into a large variety of things, including esters and other compounds that are used in all kinds of different areas of the chemical industry. So every time we talk about a new functional group, we talk about nomenclature or naming the structures. So when it comes to naming carboxylic acids, a key thing is you're going to add the suffix oic acid at the end of the name. So if I had a 4-carbon chain, that would be butane. So if the fourth or first carbon in the chain is a carboxylic acid carbon, it's just butane, but I strike that off the E and change the suffix to oic acid, so it's butanoic acid. Obviously, if there are functional groups, that's going to obviously affect the name. We want to start the carboxylic acid carbon as position 1. We want to try to include that in our parent chain as often as possible. And when we number, we want to give that the lowest number we can, just like we did for the aldehyde. And so that puts my two methyl groups on carbon 4 and this hydroxy group on carbon 5, so it'll be 5-hydroxy 4,4-dimethyl pentanoic acid, because there's 5 total carbons in the parent chain, which makes it pent, and the oic acid suffix indicating carbon 1 is a carboxylic acid. I don't need a 1 in here because it's implied. If there's no locant or number to tell me where the carboxylic acid group, it's implied that it would be on carbon 1. Tons of different common names. So this would be methanoic acid, but the common name is formic acid. This would be ethanoic acid, but the common name is acetic acid. So some of these have such common names, and they're still used very frequently. You just want to be familiar with those in general. Be familiar with the idea that some of the shorter chained carboxylic acids have names that are different from the IUPAC names, and they're just still used because they've been used for so long. Occasionally, you'll be treating the carboxylic acid group as a substituent. Now, I probably wouldn't give you an example that requires you to do that, but in this case, since I've got 6 carbons in the ring, I could use that as my parent, and then I could put the carboxylic acid group at the end of the name to indicate that that's connected to the ring. And to me, that seems kind of weird. I don't know why they set it up that way. Normally, the parent is always at the end of the name, but here they put this carboxylic acid at the end to show that that's connected to the parent. So I would generally avoid setting things up that way, and much more easy to just make a slight modification to the system we already know, which is to include the carboxylic acid carbon in the parent name and then use the oic acid suffix at the end. Sometimes a compound will have 2 carboxylic acids, and so the suffix will then be dioic acid. And I think they just think it sounds a little better in this case to avoid striking the E off the end. Right? So if I had a 5-carbon chain and just 1 carboxylic acid on the end, that'd be pentanoic acid, right? Pentane, but I don't have the E there. Pentanoic kind of like rolls off the tongue. Pentanoic acid's easy to say. If I had pentandioic acid sounds kind of weird, so they put the E back in, so it'll be pronounced pentane dioic acid. But I mean, the bottom line is that you are able to write the name correctly. So if there's 5 carbons in the parent chain, that's where you get the pent from. There's no alkene, so it's not pentene or pentyne. It's pentane dioic acid, and that implies that the carboxylic acids are on the ends of the 2 carbons, the 2 end carbons of the chain. Some of these dicarboxylic acids have common names, like succinic acid, oxalic acid, and malonic acid. You don't have to memorize those. Just be aware that, again, some of the shorter chain structures are still known often by their common names because those common names have been used so much for so long. All right, so we can use that now to name the structure from the quiz. Now, a couple groups noticed that there are some chiral carbons here, but since I didn't tell you whether I have a solid wedge or a dash wedge, you can't determine if those are RRS configurations. So let's just change this a little bit. Obviously, in your quiz answers on your Google documents, I won't expect you to label RRS for either of these because I didn't give the information you need to do that. But let's just imagine the structure had a couple solid wedges here at those chiral centers to make it a little bit more complete. So when I'm finding the parent name here, I want to include the carboxylic acid carbons. So even though I can find a longer chain that doesn't include those, based on the naming system we've learned and what we just talked about, I want to include those in the parent chain, which I now see has 6 carbons, and then I can name these other groups as substituents. So I've got 6 carbons, which would be hexane, and I've got a carboxylic acid on carbon 1 and 6, and so if I write hexane dioic acid, that would imply that structure. So if these two groups here I've circled weren't there, it would just be hexane dioic acid. Or we want to name these substituents. I've got one on carbon 2 and one on carbon 5. So it's going to be a 2,5. And what is that substituent? Well, what's connected directly to the parent chain is a 1, 2, 3, a propyl group. And what's connected to the propyl group are two chlorines on carbon 3. So the name of the substituent would be a 3,3-dichloro propyl. The propyl comes last because that's what's connected to the parent chain. But this whole thing has to be in parentheses because the whole thing is the name of this entire substituent. And I've got two of those. I've got a propyl group on carbon 2 of the parent and a propyl group on carbon 5 of the parent. And both those propyl groups have a dichloro on their carbon 3 respectively. So that would be 2,5,3,3 dichloro propyl hexane dioic acid. So this is what we're looking for your quiz answers. If we did have a solid wedge here though, let's take a look at carbon 2. We're going to have to prioritize the groups here. So if the chlorines weren't here and the rest of the structure weren't there, there wouldn't be a chiral center because these two propyl groups on either side would be equivalent. So here I've got a couple chlorines, and over here I've got another carbon or another carbon. So when I'm prioritizing away from this chiral center, the top priority is obviously here because there's oxygens directly connected there and they have a higher atomic number than carbons. The hydrogen here is the lowest priority. But distinguishing between 2 and 3, they're equivalent out this far, they're equivalent out one more carbon. The next carbon is a carbon in both cases, but that carbon over here is bonded to chlorine, whereas over here it's bonded to carbons. And chlorine has a higher atomic number. So this would be 2, and this would be 3. So I'd go from 1 to 2 to 3 and find that it's counterclockwise. And when it's counterclockwise and the fourth period group is pointing away from me, that is an S configuration. So I've got 2S. And the other chiral center is carbon 5. So I want to look at that carbon, at carbon 5. There is a 1, 2, 3 carbons and then 2 chlorines. There's a hydrogen pointing away, 1, 2, 3 carbons, and then another carbon which continues the rest of the chain, and another carbon here that's bonded to the OH. So the prioritization will be the same. Priority 1, priority 2, priority 3. And so this will be going 1 to 2 to 3. Also counterclockwise. And with the fourth priority group pointing back, that makes that one also S. All right. Make sure you let me know if you have any questions about that. So let's look at carboxylic acids in a little more detail. We talked about these a lot actually in OChem 1, in chapter 3 when we talked about acids and bases, proton transfers, and pKa values. So some of this is going to be a review, but it's really going to be a nice introduction to this function group so that we can talk about the reactions that they undergo next week. So we know because the carbon is sp2 hybridized, it's got a trigonal planar geometry, which means it's going to be flat. We talked about this in the context of the IR spectra last semester. We said normally an OH stretch is a pretty strong bond, and it takes about 3,400 to 3,500 inverse centimeters of infrared light to stretch that bond. But if the OH is part of a carboxylic acid group and it's around other carboxylic acid groups, these things can form this dimer, It's nicely set up for the large partial negative and large partial positive on one carboxylic acid group and another to actually line up and form two nice strong hydrogen bonds. And because those form readily and are especially strong, the hydrogen bond that is, it weakens the OH bond. And in reality, these OH bonds occur closer to around 3,000 inverse centimeters. So it's not as strong of an OH bond if the hydrogen starts to get pulled away and form and get involved in a stronger hydrogen bond. So we definitely know these groups can hydrogen bond. They can hydrogen bond to one another, and that means it takes more energy to separate them from one another and turn into a gas, which is why they have relatively high boiling points compared to other structures that can not hydrogen bond, or in the case of isopropanol, it can hydrogen bond, just not form as many hydrogen bonds to neighbors as the carboxylic acids can. So we see a significant difference there in their boiling points. Right, so we definitely don't want to lose track of how the hydrogen bond affects the physical properties and the intermolecular attractions of these structures. We also know that carboxylic acids are acids. It's right there in the name of the functional group. And what makes it an acid specifically is that if the base is around, the base can pick off a proton. And when the electrons stay behind, the key thing is they're stabilized through resonance, as well as the element holding the negative is a relatively electronegative atom. It's not a very large atom, so some atoms can stabilize a negative a lot better than oxygen, but it's still, with the number of protons it has in its nucleus, better than nitrogen or hydrogen or carbon in stabilizing a negative charge. So if we want to look at the equilibrium of an acid-base reaction and determine which side is favored when it reaches equilibrium and by what degree, we would look at the pKa value. So we can say this is approximately 100% because when the oxygen of the OH minus picks up a proton to produce water, and we look at its pKa, which I believe is around 16, versus the carboxylic acid, which has a pKa of around 4 or 5 usually. There's enough of a difference, 10 to 12 pKa units. And so if you remember, if you have the pKa of the weak acid on both sides of the equilibrium favors the one with the higher pKa, and that one is going to be favored by an amount that's equal to 10 to the difference of the pKa. So in other words, we would subtract the pKa, so it'd be like 16 minus 5, get 11, and that means there's going to be 10 to the 11th more products than reactants, and so that's why it's effectively 100%. It's not exactly 100%, 99.999, etc. percentage, because there's so much more product than reactant based on the big difference between waters and the carboxylic acid's pKa. So we know any strong acid like OH minus will readily deprotonate virtually every single molecule of a carboxylic acid. If you have water as your base, which is obviously much weaker as a base than OH minus, then the water would pick up the proton and produce H3O plus. The pKa of H3O plus is closer to 0 to 1. And the pKa of carboxylic acid, as you can see, is usually around 4 or 5. So this one's closer to 5. So now, with water, we know that the carboxylic acid is a weak acid, right? So we learned that in Gen Chem. Carboxylic acid is the most common type of weak acid. What makes it weak overall is when you put it in water specifically, the equilibrium does not favor the product side. And in this case, you'd have about 10 to the 5th more reactants than products. So 10 to the 5th to 1, that's still producing a fair amount of products. Not really that much compared to the reactants, but it's enough to affect the pH of the solution. Right? And that's why we get pHs usually around, somewhere lower than 7, because we're producing significantly more H3O plus than would normally be present in pure water. So overall then, when we look at the pKa of carboxylic acids, they're typically roughly halfway between the strong acids that have very negative pKa's and the alcohol functional group that's a much weaker acid, because when it loses a proton, electrons stay behind. The negative charge isn't stabilized by resonance like it is in the conjugate base of the carboxylic acid. So when you have a carboxylic acid and it loses a proton, its pKa is relatively low. It's not nearly as low as a strong acid, but it's relatively willing to give up a proton because when the electrons stay behind, the negative charge there is stabilized by resonance with both oxygens, as well as induction, because this oxygen pulls electrons away through induction, creating a large partial positive. When the electrons stay behind after that proton goes away to create a negative, the positive and negative form an extra attraction that helps to stabilize the negative and make it easier for the proton to be lost and not come back in, and that contributes to the relatively low pKa value of the carboxylic acid. Let's take a look at what state carboxylic acids exist in at physiological pH. So inside a living organism, depending on the tissue, the pH can vary, but physiological pH inside cells and your blood, generally pretty close to 7, right around 7.3. So if you know the pH is going to be pretty consistent, close to 7.3, because your body has its own internal buffer system. If the pH goes outside of a narrow range in certain tissues, you would die pretty quick because of how pH affects the folding of proteins and different reactions that you need to survive. So we know the pH is going to be kept in that area if this organism is going to be alive. So we can take that value and substitute it here in the Henderson-Hasselbalch equation, if you remember that from Gen Chem 2. And we know carboxylic acids have a pKa of around 4 or 5. So just for the sake of ease of mathematics, we'll put 4.3 in here for the pKa of the carboxylic acid. And then we want to calculate this ratio. So if we do that, we just subtract 4.3 from both sides. 7.3 minus 4.3 gives me 3. That will give me the log of the carboxylate. I'll just draw the structures here. Versus, or over the acid. So then to solve for this ratio, I'll just take 10 to the power of both sides to get rid of that log. And so that means there's 10 to the third of the carboxylates for every one carboxylic acid, right? 10 to the third is 1,000, or 1,000. So basically here, the way this boils down is 1,000 equals the ratio of the carboxylate divided by the carboxylic acid is about 1,000 to 1. So for every one carboxylic acid group in your body at physiological pH, 1,000 of those molecules are in the form of a carboxylate. So normally we don't think of a carboxylic acid as being a strong acid. Most of the molecules in water don't give up protons to produce a negative charge. But this isn't water. So you should be aware, and this translates to any instance where you might be dealing with a biochemistry course or certain biology courses that deal with molecular structures. If you have a carboxylic acid at physiological pH, many more of the molecules are going to be in the negatively charged conjugate base form than will be in the carboxylic acid form. So there's a little flashback to Gen Chem 2 and a little preview to anyone who might be taking a biochemistry course. And so here's a molecule that's very relevant to metabolism. Pyruvate is the dominant form of this structure because at physiological pH, the equilibrium favors the negatively charged side over the neutral side in this H plus wouldn't be all on its own. It would be connected to, the buffer, whatever the buffer is that's present there. All right, so a couple other factors that affect the acidity of carboxylic acid so that we can make sure that we have the ability to rank the acidity of carboxylic acids. We know that we can use the acronym, talked about this in OChem 1, to rank the acidity of substances, including carboxylic acids. So S stands for solvation, C stands for the quantity of charge, A stands for the atom carrying the charge, R stands for resonance, and I stands for induction. So when it comes to carboxylic acid, if I'm dealing with a carboxylic acid, most of these are going to be the same. No matter what the R group is, when it loses a proton, and I'm trying to decide how acidic it is, the main question is, how readily is it going to give up this proton and stabilize its negative charge on the conjugate base? The more stable the conjugate base is, the more the acid will react. The lower its pKa, the stronger the acid. So what stabilizes the negative? Well, there's resonance in every carboxylic acid. The atom stabilizing the negative is always an oxygen. The quantity of charge is always -1. So solvation may be a factor, but most of these other factors are the same for all carboxylic acids. So if we're looking at subtle differences, induction is one of the major factors we want to consider. And the way induction works, as we know, is if we have something highly electronegative, the more of that we have, the more it pulls electrons away. And so that will attract electrons and create an even greater positive here. Why is that important? Because if I have a large partial positive on the carboxylic acid, it can act to form an attraction to the negative that forms in the carboxylate conjugate base, and that stabilizes it and makes it more able to give up a proton. So we see the pKa going down a little bit each time. Every electronegative atom we add increases the amount of positive here, and it stabilizes the negative that forms on the carboxylate, so it's more able to donate the proton and form the negative when the negative is more stable. If you put the electronegative group farther and farther away, the effect it has on the pKa is smaller and smaller. And so we really only see a real significant effect when the electronegative atom is on the very next carbon out from the carboxylate. This trend here shows a similar situation. The numbers don't vary a lot, but there's a difference on one end of the scale compared to the other. So basically what we're saying here is, if I have an aromatic ring and a carboxylic acid, groups that are maybe quite far away, like a nitro group at a pair position, could really affect the acidity of that proton. And so it seems weird that something so far away can have that impact. But because the ring is conjugated, all this is connected through resonance. So the idea here is, if this electron pair swings out to the oxygen, that will attract this electron pair out here and this electron pair over here, and that creates a partial positive there. So as the electrons swing out, it creates a partial positive at every one of these positions. But the key is putting the positive here attracts electrons from the carbonyl, which creates a little bit more positive there. And that helps to stabilize the negative that forms if it reacts as an acid. So it'll more readily react as an acid and have a lower pKa if the negative that results in the conjugate base is somewhat stabilized by an attraction to a positive that forms due to the presence of that electron withdrawing group. So the less effective the group is at withdrawing electrons, the less it can stabilize the negative. And in fact, if I have an OH, which is the opposite, I can draw that one as well. So an OH can withdraw electrons through induction, but that only puts a partial positive there. So if I have a carboxylic acid para to that, and I'm trying to imagine how much this carboxylic acid is going to be stabilized once it produces a negative, well, a partial positive all the way over here is not going to impact that in any real significant way. So the electron withdrawing nature of that oxygen isn't really relevant to the reactivity of the acid or the pKa of the acid. What is relevant is how the lone pair can shift in here and push electrons through the ring onto this carbon. And so that negative is going to repel electrons and create a tiny negative there. Putting more negative next to a negative is only going to make it less stable. So the molecule has a higher pKa and is less likely to donate a proton if the resulting conjugate forms a negative that's not effectively stabilized and actually slightly destabilized by the presence of that OH group through resonance. All right, so that should then allow us to rank these structures here from the next quiz question. So what I'm noticing here is I've got a couple carboxylic acids, but this isn't not a carboxylic acid. So I got to think about how is the sulfur going to affect it, being sulfur versus oxygen. And then what I see in D is an extra carbon here. So this may look like a carboxylic acid to you, hopefully it doesn't, because a carboxylic acid requires the OH to be bonded to the exact same carbon that is the carbonyl carbon. Here I've got 2 carbons in there instead of 1. That makes a big difference. So anyway, though, I want to use this acronym. And solvation is only going to be a major factor if some of these are in a different solvent or no solvent. There's no indication of that, so I can assume that all these are in the same solvent, probably water. If it doesn't say, I would assume water is the solvent I'm measuring the pKa in. So if they're all in the same solvent, probably the solvation then becomes the least relevant factor. If these were in different solvents with different polarities, I mean the solvents had different polarities, solvation would be the major factor. That's why we put it in the front sometimes. So it's a little tricky here, but if I write it like this, now I can look at these factors in order of priority. So I want to look first at the quantity of charge. Well, they're all neutral, and if they were to each act as an acid, they would produce a single negative charge in each case. So since they all produce the same quantity of charge, I can't use that factor to distinguish which will be more likely to give up a proton, right? If I had something like this as well, like maybe I had something that started off with a positive, well, that's going to have a lower pKa than any of these because it's going to be very likely to give up a proton if it results in something that has, that isn't as unstable because it doesn't have the same charge the other ones have. So that's what we're talking about when we're talking about quantity of charge. So that factor doesn't distinguish between these 4 because we don't have anything that has a different charge. They're all the same quantity of charge. So the next factor, factor number 2, is the atom carrying the charge. And that's where C stands out compared to A, B, and D. So is sulfur better at stabilizing a negative versus oxygen? So, I mean, I have to recognize that some of these are in resonance and that, in this case, the negatives, not just on sulfur, spread out over the sulfur and oxygen, but spreading out the negative in part over the sulfur versus just on a couple oxygens does stabilize the negative. Right? So when you think about the atom, the larger the atom is, the more it should stabilize a negative because the less of an imbalance creation is created there for the charge ratio. Right? Sulfur's got a lot more protons, so when I add 1 extra electron, it doesn't affect the negative to positive ratio as much as it would if I had a smaller atom. So that suggests the lowest pKa one here is going to be C. Because the sulfur stabilizes the negative, the original compound is going to be very able to lose a proton to produce such a stable negative charge. So then the next thing I look at is resonance. I see the negative is stabilized by resonance in every one of these structures except D, or the conjugate base of D. Because there's an sp3 hybridized carbon here, there's no p orbital overlap with this p orbital, there's no way to stabilize that through resonance. So this negative is way less stable, and that means the acid is very weak. This is more like an alcohol. The pKa here can be closer to 15 to 20 rather than 4 or 5 that we normally see for carboxylic acid. So this is going to have the highest pKa due to the negative not being effectively stabilized without resonance. Next thing we would look at is induction. In this particular case, the only two we have left to rank are A and B, and they both have R groups, and those R groups would both be very mildly pushing electrons in, creating a slight negative here. But it's going to be pretty similar for both of them to be able to do that. So that's not going to help me distinguish between them. The orbital as a factor, also the lone pair is going to be in a p orbital because it needs to overlap with the other p orbital through resonance. So the type of orbital holding the negatively charged electrons that are making the unstable formal charge is the same in both of those structures. So I can't use that to distinguish between them. And so then the last factor is solvation. And solvation has to do with the solvent molecules forming intermolecular attractions with the charges, right? So whatever the solvent is, it's going to have either a permanent dipole like water or maybe a temporary dipole if it's nonpolar. Either way, it's going to be some quantity of charge on the solvent that can surround this negative and attract to it. So whatever the solvent molecule is, the more solvent molecules can come around and bring an area of partial positive next to the negative, the more stabilized it can be. And so that can occur for both these two structures as well. But here's where the R group is relevant, because the larger the R group is, the more it's going to block out some of the solvent. If I have a small R group, then more solvent molecules can surround that and really form more attractions and stabilize the negative. The more the negative is stabilized, the more readily the acid will give up a proton to produce the negative. So if everything else is the same, and the only difference here is a bulky R group versus one that's not bulky, the bulky one I expect to block out some solvent from forming an attraction there. So it's not going to be as likely to produce a charge if the solvent can't get in to stabilize the charge as well. So A would have a higher pKa than B for that reason. Hopefully that makes sense. If not, let me know. We'll talk about it in more detail. And then the last thing we're going to talk about quickly here, I know we're almost out of time, pretty much out of time, but just to tack on a little bit more here. To review, we've talked about a couple reactions that produce carboxylic acids. One reaction we talked about last semester, we haven't talked about lately, is a strong oxidizing agent can completely cleave an alkene and then oxidize the two carbons of the alkene fully to carboxylic acids. That is assuming there are protons here to be removed, right? So the R groups don't get removed, but protons can. So that's a reaction you want to be aware of if you're trying to form a carboxylic acid. Probably this wouldn't be very useful in syntheses because it breaks down the number of carbons. Usually we're trying to build up the number of carbons to build up the complexity of the structure. So other oxidizing reactions, so these are more recent. We know you can react a primary alcohol with a strong oxidizing agent. That will remove the protons and convert that to a carboxylic acid. We know as long as there's one proton or more at a benzylic position, that's the benzylic position is one away from a benzene ring, that same strong oxidizing agent, which I could also write as H2CrO4, chromic acid is what forms when these two react together. The chromic acid would remove that proton and the carbon groups and leave just one carbon off the ring to make carboxylic acid there. So you want to be aware of that reaction we discussed. And then before we finish today, there are two more reactions that you can use to make carboxylic acids. And these are reactions we're going to talk about in more detail as we go through, but just to introduce you what they are and how they work. One is the hydrolysis of a nitrile or cyano group to a carboxylic acid. So any time I have a CN using H3O plus and water and heat, I need a fair amount of heat here because the transition state energies are kind of high, I can convert that carbon that was triply bonded to a nitrogen into a COOH. And we talked about that a little bit today. We're going to see the full mechanism for that, I believe, here coming up in probably next week. Sometimes this overall reaction is something you would see because we see a lot of alkyl halides. We know that's a good leaving group. So if you want to convert a molecule that has a certain number of carbons in an alkyl halide into a structure that has one additional carbon, one way to do that is to have the cyano group push out the halide. And then if you want the CN, that's fine. If you want a carboxylic acid, you can hydrolyze that with under acidic conditions. Another way to make a carboxylic acid is using a Grignard. Right? So we know the Grignard forms an attraction with the magnesium, but mostly the carbon owns those electrons, so it's pretty unstable with a negative charge. And CO2 is a pretty good electrophile. It's not polar, but the carbon itself, due to the electronegativity differences here, is carrying a large partial positive. It makes a decent electrophile. So if the Grignard is surrounded by CO2 bubbling through the reaction, it can attack that carbonyl carbon, push electrons onto an oxygen. That makes a carboxylate. And so then in a second step, you would add H3O plus. We can't add it all together because the Grignard would simply pick off a proton from the H3O plus. So again, can't do the Grignard if there's any product source around. So the Grignard would have to react with the CO2 first, then in a second step, the H3O plus could be used to protonate that. So here's an example, a specific example of how that would work. And here are two more examples. So the final quiz question of the day is just an application of those last two reactions. So here, if I have an alkyl halide and I react that with magnesium, that should convert that into Grignard. If I use CO2 then, the Grignard should attack that carbon, push an electron to the oxygen. That will produce a carboxylate, and then the H there is just used to donate a proton. So that would pick up a proton, electrons stay behind to make a water, and that would produce a carboxylic acid. So one other thing to note about this, as we said a moment ago, is if we count the carbons, there's 6 in the ring, 7, 8, 9. In the final products, the carboxylic acid carbon is an extra carbon. So both of these reactions, they're starting with the alkyl halide and producing a carboxylic acid, increase the number of carbons by exactly 1. Here, the CN minus is a great nucleophile. It would attack here. But in this case, it's too crowded to attack right away. So the Br would have to leave first, which would produce both a tertiary carbocation, and also that would be stabilized through resonance. Then the CN minus could attack. And then these conditions, we'll talk about the mechanism for this later, so don't worry about it right now, would hydrolyze the CN. So this carbon here would become a carboxylic acid carbon. And that would also, again, increase the number of carbons by 1 from what we had initially. So I'll be checking through your quiz answers and giving you feedback on that as well. All right, so I know that's a lot. Lots of good practice for you to work through. Please let me know if you have any questions about it. Next week, obviously, we'll be taking our exams on the content we learned this week, but then we'll be getting into Chapter 21 in more detail. And we'll start talking about some derivatives of carboxylic acids like esters and anhydrides and acid halides. So you want to be well prepared for that. So check out the videos and read the relevant sections for Monday. And hope you all have a great weekend.